So now, we've been looking at the NAND gate in other videos, and we're coming back to it, but this is the 74HC132 integrated circuit, not the 00. And so this one's a Schmitt trigger. So what that means is we have both inputs high right now, the output's low. That's the only way the output's low. So right now we're picking up stray signals. It's bouncing high and low, as is the output. But in any case, if one input or the other input is low, you're going to have a high output. Or if they're both low, doesn't matter. Now, we're going to set this one back high. So this is a Schmitt trigger. With the 00, when I got to the trim pot to a certain point, the output didn't really know what to do. But here, we don't have that problem. There we go. Went right from high to low. And now when I go down, it will go right, the output will go right from high to, or low to high, I mean, right there. So there's a middle ground hysteresis where it could be either one, and it jumps from one to the other instantly. So now we come to the schematic diagram I drew for the 74HC132 demonstration circuit. So it's a NAND gate. There's 4 of them on the integrated circuit. We only used one for the example. But I used a piece of wire as a jumper to go directly from positive supply to negative supply. But when it was floating in the air, then we were getting stray signals to the input. So it could be either high or low. Something to be aware of. But you'd want a digital switch that jumps back and forth. But in any case, since this NAND gate integrated circuit is a Schmitt trigger version, unlike the 00, which is probably more common, we can give a changing voltage. So if you go down far enough, that'll be a low input for sure. But you work your way up, sooner or later you'll get high enough where boom, all of a sudden you have a high input. But there's hysteresis. You got to go down a bit further before it will turn into a low output. So there's a middle ground region where the input could be either high or low, but it'll definitely be high or low. So now, in the first 2 shorts of this longer video, we looked at this Schmitt trigger NAND gate, how it kind of works. So we're going to talk a little bit more about the output right now, because we didn't have time to focus it on before. So when both inputs are high right here, definitely high, that's when the output's low. That's the only time the output's low. If either one of them are low, then the output's going to be high. It's going to connect to the positive supply right there. But in any case, I use this in a lot of my circuits, but I'll review it really quick. When the output is low, so that means both inputs are high, that's when the blue LED lights up. You can see we got 5 volts right there headed to ground right there. Now when the output is high, so one or both of the inputs would be low, then the red LED will light up. You can see that current path right there. And again, blue LEDs are brighter than red LEDs, so I'm limiting the current more with the blue LED. And quickly going over some extra info on the diagram I drew for this. We got the NAND gate right there, and that's how the output's going to be. If any input's low, the output's high. You need both inputs high in order for the output to be low with the NAND gate. Now with this integrated circuit, check the data sheet, but that gives you an idea of the power output capabilities. Usually with these integrated circuits you want to work with 5 volts. So a lot of times you have to. So in any case, of course you got to power the integrated circuit right there. And the ones that we're not using, the logic gates, we tied their inputs to one of the supply voltages. So I did that to the positive supply because I got a lot of these yellows. So they're a good indication that it's to the positive supply. That just locks their output into place to avoid oscillations. And as you can see, we got positive supply to pin 14 there, and the negative supply to pin 7. We need both inputs high for the output to be low.